Thank you, Damien, for an incredibly flattering introduction. and thanks for having me down here for the day to get to meet some of you and chat about my research. And I look forward to the conversation we'll have after my seminar as well, so we can get into some of these questions in a little more depth and hear your thinking on some of these topics as well. So I'm going to talk probably about 45 minutes about my own research and survey of a broader set of research that has been published since 2014, which is when the last Intergovernmental Panel on Climate Change report came out. And for those who have perused it or haven't, the IPCC reports have three sections, three working groups that bring together interdisciplinary teams to study the science and drivers of climate change in the first section, the impacts and adaptation in the second, and mitigation strategies in the third, which is where my work focuses. So how do we tackle greenhouse gas emissions and reduce, hopefully, the long-term impacts of climate change? And central to that challenge is the electricity sector, and I'll explain why. And so that's where much of my work focuses, which is using quantitative modeling to explore how the power system, electricity system might evolve over the next several decades, what influence new technologies might have on that evolution under this sort of uncertain environment that we face, and what policies might accelerate our progress towards a zero-carbon energy system. I think hopefully we'll post these slides later, so I've put some resources that are my recent work and some others that are where much of this, the insights in this presentation are drawn from, so you can pull those up in the future. All right, so getting to zero. Why do I say zero? So this chart here, which is from a great paper by Glenn Peters and others in Nature Climate Change last year, looks at what we need to do to keep on track to the commitments made in the Paris Agreement on climate change, which was to try to keep average global warming to no more than 2 degrees Celsius, and ideally lower if possible. And this graphic shows the trajectory for global carbon intensity, which is the ratio between CO2 emissions and the amount of energy we consume to power our economic activities. And the different lines, different dark colors are averages of the lighter color squiggly spaghetti lines behind there. But each of the colors correspond to when we take serious policy action to peak and start reducing emissions, whether that occurred historically in 2010, in the future in 2020 or 2030. And then the historical baseline, historical in black and baseline in gray. And what you see from all of these is that they effectively need to fully decarbonize our energy supply systems by sometime in the second half of the century. So regardless of when we start to drive down emissions, our ultimate goal is zero emissions from energy activities. And in fact, in some of those scenarios, you see the total is actually negative. How do we get to negative emissions? Well, those scenarios rely on either biomass combustion, where we capture the CO2 emissions from the biomass, so the biomass absorbs CO2 from the air, and then we capture the combustion emissions and bury it, which can lead to negative emissions. Or we simply do things like afforestation or other measures to directly remove CO2 from the atmosphere and offset the remaining emissions elsewhere in the economy. So the goal for the economy-wide, for all sectors of the economy, and for the globe is to reduce emissions to zero by sometime around 2060 or 2070 if we want to keep on track to 2 degrees Celsius. But electricity is the linchpin in that challenge, and developed countries, the rich world, including the United States, has to proceed fastest and furthest of any sectors to drive emissions down. And so electricity is the linchpin in many of these strategies for global decarbonization and really has a twofold challenge. The first is that, as I mentioned, it has to drive emissions down further and faster than other sectors like transportation or agriculture or heating in our buildings. And in the developed world, really reach zero emissions sometime around the late 2040s or 2050 timeframe. And it has to do so at the same time that we dramatically expand the use of electricity to fuel other economic activities and therefore displace consumption of oil, coal, or gas in things like transportation or heating with carbon-free electricity. So even if in the developed world energy efficiency measures keep overall energy consumption about flat, and of course it'll grow in the developing economies, electricity demand may increase dramatically, in some scenarios roughly doubling, as we fuel more of our economic activities with electricity. So think about purchasing an electric vehicle or converting from an oil or gas-fired boiler to heat your building to an electric heat pump system or a ground source geothermal heat pump system that uses electricity for heating and cooling. So this is the twofold challenge, driving emissions to zero and doing so in a way where we can expand electricity. And that means, because both aspects of the challenge are important, that if we fail in decarbonizing electricity, it can imperil overall efforts to decarbonize the economy as a whole, and therefore our efforts to confront climate change. And second, if we fail to do so affordably, so say we succeed in the rich world in decarbonizing electricity, but in a way that dramatically increases the cost of electricity, that will do two things. One, it may slow dramatically the expansion of electricity as a cost-effective substitute for heating fuels and transportation fuels and industrial inputs in those other sectors, because electricity will be much more costly compared to oil or coal or gas in those sectors. And second, if we do so in a way that only rich countries can afford, the strategies that we pursue to decarbonize electricity in the United States or elsewhere cannot be copied by developing countries that don't have the extra income to afford to spend on those kinds of costly mitigation techniques. So we have a challenge. We have a challenge to not only decarbonize electricity in the developed world, but to do so rapidly and affordably. And if we fail in either of those tasks, we may fail to confront climate change. The good news is that we've seen tremendous progress for wind, solar power, and battery energy storage just in the last several years that have made these technologies incredibly competitive in a growing number of locations throughout the world. So this is just a few headlines from the last couple years about Xcel Energy in Colorado, which is the major utility in Colorado, receiving very low-cost bids for energy storage and renewable energy resources that are actually starting to make renewables cost competitive with new gas-fired generation and even some of their existing coal-fired power plants, where it makes more sense to shut them down and backfill that energy with new renewables. Forbes reports on an analysis from Europe that found that renewable energy will be consistently cheaper than other sources of fuels, basically all over the globe by the 2020s. And we're seeing electric batteries for energy storage, mostly lithium-ion storage, become a competitive alternative to building peaking power plants that are used traditionally only to meet our peak demand. And what's behind that is a really tremendous decline in the price of all three of these technologies just since 2009. They've all fallen in price by about 2/3 or about 70%. And this has been one of the most remarkable pieces of improvement in the overall landscape for decarbonization that I've seen in my career. If you had asked me in 2008 whether we'd be seeing wind or solar projects bidding in at subsidized prices, but still even unsubsidized prices that are at 4 or 5 cents per kilowatt hour, I would have said no way. Because at that point, if you could get a project that was under 10 cents, that was a great deal. And so we're seeing these just dramatic improvements that have made the core economics of wind, solar, and batteries so much more attractive for investment by individual companies like Google or Facebook or Apple who are investing in these kinds of projects, or even utilities who all over the country are saying, look, we're done building new fossil plants, or we're only going to build those to replace our existing coal fleet, and we're going to be harnessing a mix of gas and renewables to drive ourselves away from coal and drive down emissions. And if you look globally from that same paper by Peters et al. At the progress we're making in terms of deploying wind and solar, and then biomass is the other renewable resource that is widely adopted, you can see the black line here is tracking, which is the actual deployment, is actually tracking with the kinds of deployment rates that you would need to see to stay on track with that 2 degrees Celsius Paris commitment. So we're making progress and keeping pace with wind and solar. You will, however, notice that the pace of progress has to continue to accelerate to stay on track. So we have to keep bending that curve upwards and accelerating the deployment of those technologies to stay on pace globally. The downside, or the discouraging news, is that the rest of the technologies that fill out the low carbon team that we were expecting to help keep us on pace to those objectives are falling behind. So the other 2 large sources of low carbon energy that are counted on in virtually all scenarios are an expansion of nuclear energy and carbon capture and storage, which would allow us to capture the emissions of CO2 from fossil fuels and permanently sequester those or use them for production of other industrial materials or fuels. And as you can see, nuclear energy globally is basically stalled, where the construction of new nuclear power plants in places like China, the Middle East, and elsewhere are simply treading water and keeping pace with or offsetting the reduction or the retirements in capacity of older nuclear power stations from rich countries, such as the Pilgrim nuclear power station up the road in Plymouth, which will be retiring in the spring of next year. And carbon capture and storage, despite much focus from the technology, policy, and climate communities over the last decades, is essentially still at a pre-commercial stage, where a number of demonstration projects have moved forward, but no commercial scale adoption has proceeded at anywhere near the pace envisioned. And you can see the rather steep uptick in the use of CCS in some of these scenarios, which appears rather implausible at this point. And that's largely driven by the fact that many of those scenarios depend on us having negative emissions from biomass. So not only we're using carbon capture to capture emissions from fossil fuels, but also from biomass plants, and therefore help drive negative emissions. So the use of CCS is far behind track for most of those scenarios. And if you're paying attention to the news, you've seen really discouraging headlines around progress towards building some of the first large-scale nuclear or carbon capture projects in this country, at least, as well as in Europe over the last several decades. So there were 4 new nuclear power stations, AP1000 reactor designs from Westinghouse, that were under construction at 2 sites in South Carolina and Georgia that were far over budget and far delayed, to the point where the costs incurred drove Westinghouse, the manufacturer, into bankruptcy, caused one of those plants, the South Carolina plant, to have them pull the plug after spending roughly $25 billion on a big hole in the ground at the end of the day. And the project in Georgia is now, actually this week, they're once again debating whether to continue construction of that or to cut and run. And a similarly large setback for a high-profile coal gasification and combined cycle power plant that would have captured its CO2 emissions, built by Alabama Power, or Mississippi Power, sorry, where they suspended work and effectively ended up spending a whole bunch of money to get a very expensive natural gas-fired power plant that doesn't capture its CO2 emissions. So this is the kind of discouraging headlines you've been reading about carbon capture and about nuclear, at the same time that we see all kinds of positive news about renewables. So with that landscape, there has been a lot of debate recently, and I think in the classes those of you who are in the class have been reading some of this debate as well play out over the last several years among scientists and policymakers and advocates about whether we should be putting all of our chips behind renewable energy, the apparent winners in the current race. Should we go all in and bet heavily on wind and solar to carry us to the finish line and to decarbonize our electricity supply? And I think, and I'll spend most of the rest of the conversation talking about whether it makes sense to place that bet given what we see today or not. So the mental model behind, I think, behind much of the exuberance around renewables is depicted here. And I have to admit this was my mental model for many years, including when I worked at the Breakthrough Institute on public policy recommendations, which is that solar, if we go back to 2009, or earlier, solar was much more expensive than fossil fuels as a source of electricity. And therefore, if we left everything to the market, no one would invest in this technology. They would invest purely in new fossil generation. But if we used public policy to help subsidize that above market cost, or that gap between the solar and the coal or gas, we can make it an attractive investment opportunity for the private sector. And if we did that, we could drive deployment and scale up and improvement of this technology such that over time, what are known as experience curves kick in, which is that as we drive more deployment, we drive economies of scale in manufacturing, we drive incremental improvements in learning by doing in the manufacturing process or installation process, and we induce additional research that steadily improves the performance and cost of these technologies. And we've seen this in a variety of sectors, from cell phones to shipbuilding, to aviation, to microchips, and as well as strong learning curves or experience curves for wind and solar. And so as you can see in the dotted line, as we've driven cumulative global capacity of solar up in a relatively exponential manner, we've seen the cost for solar steadily fall. And these ratios tend to follow a logarithmic curve, where for every doubling of cumulative capacity deployed, you get some reduction in the cost of the core technology. So that for the case of solar, we've seen that cost come down by roughly 20% for every doubling of solar deployment. So the idea was, let's use policy for a temporary period of time to drive deployment of this technology, drive down its price to the point where it beats fossil fuels on cost. This was my mantra at the Breakthrough Institute as the head of their policy, their energy and climate policy team. My mantra was, make clean energy cheap. Make it cheaper than coal, make it cheaper than gas, make it an attractive option for new deployment. And if we could do that with temporary policy, we could start a self-reinforcing loop, which would then lead to a tipping point where all of a sudden the private sector would lead and public policy could fade into the background. And we've actually hit that tipping point, which is tremendously exciting. And so, as we see, new coal-fired construction, especially, and even new gas, as of the last year or so, solar is now cheaper across much of the country. Obviously, there's a big bar around this depending on how good the solar resource quality is, and I can show the same kind of graphic for wind. So they're now some of the cheapest sources of energy available for new construction in many, many parts of the world. So have we won this race? Well, unfortunately, as I spent my time in my PhD studying how electric power systems work, I learned that this is a bit of a flawed mental model, this race on cost between wind and solar and fossil fuels. And I started to liken it to the idea of comparing the cost of a banana and a burger when you go to the grocery store and try to decide what you want to buy and eat for your meal that night or for lunch the next day. Knowing the price of a banana is useful information. Knowing that it's cheaper than the burger is good to know. But it's not really going to tell you which of these you want to buy because they're not substitutes for one another, right? You're not going to only eat burgers, I hope. And you're not only going to eat bananas. You need a balanced diet, and you value certain foods at different times of your day and different types of the week and different parts of your diet. And so what we've been doing when we look at charts like this is effectively comparing bananas and burgers. A solar plant is not a substitute for, or at least not a direct substitute for a coal or a gas plant. So just like a banana and a burger both provide calories, a solar farm and a wind farm and a coal or gas plant all provide electricity, but they're not direct substitutes for one another because they don't produce electricity at the same time, they don't produce it with the same reliability, and they don't produce it with the same value in the overall power system as a whole, just like these different food choices have different roles in your overall diet. So the comparison that we should be making, which actually paints a slightly more daunting picture, at least one that should motivate continual policy intervention and effort, is that we need to be comparing the declining cost of these technologies with what their own declining marginal value as we deploy more and more of these technologies in the market. So as with many things, there's diminishing marginal returns to deploying more wind or solar in the market. But it's particularly pronounced for wind or solar because all of their production is correlated, right? You produce solar output when it's sunny, and you produce wind output when it's windy, and it tends to be sunny in Rhode Island at the same time that it tends to be sunny in Massachusetts or Maine or elsewhere, and it tends to be windy even across wide areas like that, and they're correlated to produce around the same time, which means that when we have available solar, all of the solar is producing power at the same time. When we have available wind, it's all producing, and when we don't, when we need energy, it's not like deploying additional solar will help you produce power at night. So what happens in electricity markets is as we deploy more wind and solar that have no fuel costs, we effectively think about a supply and demand curve from a basic economics class. We're effectively shifting the supply curve out and adding a bunch of zero cost resources to the edge of the supply curve. And that means for any given level of demand, the price falls in those periods of time. And that means that the revenues that solar earns as you deploy more and more solar and produce more and more at that hour falls as well. And so you have this race not between the declining cost of solar and the cost of gas or coal, but between the declining cost of solar and its own declining value or revenue in the market. The same is true for wind. So this graph shows 3 different studies that looked at solar in different contexts and shows the decline in value as you deploy at different levels of market share. And so what this shows is that at 2017 costs, it might make sense to get upwards somewhere between 5 and 15% of energy from solar. But unless costs continue to fall, at that point it wouldn't make sense to deploy any further without additional public policy support or cost declines. And the same is true for energy storage, where you see a very steep cost decline. This is from one of my papers in 2016, where we looked at the value of energy storage in low carbon power systems and found that there's a relatively linear decline in the value of additional storage capacity as you deploy more and more peak capacity from storage in the system. So the first unit of storage you install in your system is very valuable. You can arbitrage the spread in prices from very low prices to very high prices and make lots of money. You can avoid the need to build expensive peaking power plants, but as you deploy more and more of it, those spreads that you rely on to buy low and sell high with your storage device to make money start to compress, and you make less revenue and deliver less value. So there are really 3 key mechanisms that drive this decline in value, and I'll give you an illustrative example in the next few slides of the main ones. So the first is a decline in the fuel saving value, or the ability of a megawatt hour of solar or wind to substitute for a megawatt hour of another fuel that has a higher marginal cost or a higher fuel cost. So I call this the fuel saving value. The second is a decrease in the capacity value, or the ability to substitute for firm or reliable capacity installed from different resources. So how many megawatts of solar do we need to deploy in terms of its peak generating capacity to reduce the need for some megawatts of a firm gas-fired power plant or a coal-fired power plant or an energy storage device. And third, an increase in overgeneration, which is that at some times we may be producing more solar or wind than we can actually consume or absorb at the time. And that has to either be stored for later use at some cost, or it needs to be wasted or curtailed, in which case it delivers no value. There are other factors that also are at play that are, I think, if you've followed this literature, are typically characterized as integration costs. So these have to do with the variability of wind or solar on different timescales, and the need to operate the rest of the grid differently in order to provide flexibility and match the output of these power plants. These are second order effects we found, so they're important, but they're smaller than these core declines in the value of the resource itself. But those are things like the need to operate your natural gas plants more flexibly, or even your nuclear plants more flexibly, to ramp up and down their output to match wind and solar on different time scales, to have more, we call operating reserves or backup capacity that can step in if we get our wind forecast wrong and have less wind for the next hour than we thought we would. We have to turn on and off thermal power plants like coal or gas plants more often. And every time you turn them off or turn them on, you have to consume fuel and heat them back up. It takes time and it costs money and burns fuel and therefore produces CO2. And you have to build out a different transmission system to connect to these things. So these are all costs that are important as well, but as I said, are generally second order to the other factors. So let's consider a hypothetical example here for New England, where I've basically made wind and solar quite a bit cheaper than they are today. These might be like 2020 or 2025 type costs. Natural gas plants cost about what they do now, including fuel. And I put in a very expensive nuclear facility. These are the overnight costs. This is about as expensive as the new nuclear plants that are being built in Georgia. And so we look at New England. And if we look at every hour of the year on the bottom, that's what our demand looks like going up and down throughout the seasons. You can see some cold snaps in the winter where demand is really high in January. We had a very cold one this winter, if you remember, for a few weeks. And then you have the peak in demand in the summer when everybody's running their air conditioners on hot, humid days. I've built a simple optimization here which doesn't have any of the kinds of operating constraints in terms of how fast your power plants can ramp up and down or the reliability they need to provide, which I include in my more detailed modeling for academic work. But this captures the core dimensions here. And I've given in the model a constraint, which is that I want 20% of our electricity to come from renewable sources. So you can see that bar up on the top here, the clean energy share, shows the percentage from low carbon sources. And it's, in this case, the model chose only solar to meet that first 20%. So no wind. Solar was the cheapest way to do that in this mix. And you can see in every hour, the yellow is the amount of solar production in each of those hours. So going up and down, daytime, nighttime, with seasonal trends. This is pretty hard to look at with all the squiggly lines. So we can reorder everything, and we can rank it in what's known as a load duration curve. So we basically take the highest hour of demand and put it in on the far side here, and then we rank order every hour of demand from highest to lowest. So it's the same hours from before, but we've just reshuffled them in time and put them from highest to lowest. And this helps us see how much total peak demand do we have, and therefore how much reliable capacity do we need. In this case, it's 34 gigawatts, or 34,000 megawatts of peak demand. And then we can see the yellow strip, yellow or green, is how much of that demand in every hour is met by our renewable resources. Okay. Then I have a number of other dials here, which will change as we move forward with a higher constraint, which show the energy and capacity value of wind or solar. So on the top, we have the energy value, and right now the energy value is 100%, and what that means is that in every hour, or every megawatt hour of generation from the next unit of wind or solar you deploy displaces natural gas-fired power plants. So it's offsetting the energy cost and fuel from a natural gas combined cycle power plant in this case. That's what I consider 100%. And you can see that where every hour here you have some brown left, which is generation from the gas plants. Okay? No hours do we have any excess solar generation, but that will change as I go forward. And then the capacity value says how many megawatts, for every 100 megawatts of wind or solar I deploy, how much do I reduce the need for firm generation on the peak side of the picture here. The capacity value for wind is 9%, meaning for every 100 megawatts of wind I deploy, I can reduce the need for gas plants by 9 megawatts. And for solar, it's 4%, meaning I have to deploy 100 megawatts of solar to reduce the need for 4 megawatts of gas capacity that's reliable and there when I need it to meet peak demand. Why is it so low? Well, it's so low because the net peak, or the period when I have the highest demand for fossil generation or non-renewable generation, is on September 8th at 5 p.m. So there's not very much solar output at 5 p.m. And therefore, even though I deploy a lot of capacity, it's not producing very much during that hour when I really need it. And this happens to be a relatively low wind period, and so there's also not a lot of wind output in that hour. All right, so let's step forward and drive ourselves towards a low carbon grid and see what changes. So now I'm increasing the requirement to 40% renewable energy or clean energy. And now we start to see some wind added to the mix because even though solar was the cheapest source at the beginning, its value has now declined enough that it makes sense to start deploying deploying wind as well to complement it in a portfolio. The marginal energy value of wind has now fallen to 91%, and for solar to 77%. And you can see in blue, there are now several hours of the year when we have more wind or solar than we need. We've completely backed out all of the fossil fire generation in those hours, and we're producing more than we can consume in that hour. And that's why the energy value has fallen, because now what this means is that 8% of the generation from the next wind farm we deploy occurs during those hours when overgeneration occurs, and 23% of the solar generation, almost a quarter, occurs during those hours. Why does that reduce the value? Well, that means that the marginal unit of generation, if I had a little bit more demand in that hour, that demand would be met by less curtailment of wind or solar that has no fuel cost. So my savings would be zero. So the fuel or the energy from wind and solar in those hours is literally worthless. Now we could install energy storage, store some of that. The storage would be willing to pay something. We can use it in another hour that has more value, but that storage itself has a cost, and it has to cover that cost by buying low and selling high. So it's not like it's going to pay a premium for energy, especially when you have people giving it away for free, and therefore the marginal bids from everybody, if it was a competitive market, would be zero. So even adding storage is unlikely to dramatically change that equation. The capacity values are the same because the net peak hasn't moved yet, but we now are wasting enough energy to meet 3% of annual demand across the year. When we go to 60%, things start to get more dramatic. We now are wasting enough energy to meet 7% of annual demand, so we've gone up by 20 percentage points in terms of the energy share, and we're now wasting enough to meet 7% of our demand. The solar value has fallen to 59% and wind to 72% because more and more of the wind and solar generation is concentrated in those hours when we have an excess, where we have the blue period. And now the net peak has moved from September at 5 p.m. to a hot August day with low wind output at 6 p.m. So you've probably experienced these days around here, right? They're super muggy. There's no wind. It's and everybody's got their air conditioning on in the evening when they get home, and the buildings are putting out the most heat, residual heat, and so that's when the peak demand period is now. And the solar output is only 2% of its capacity at that point, and the wind value is the same. So add as much wind or solar as you want, you're still going to barely affect the need for peak or firm generating capacity to meet those demands. Now what happens when we go to 80%? Well, you can see that the overgeneration starts to rise non-linearly because we have to add more wind and solar to produce some energy in the other times when we don't have overgeneration, but it's going to keep producing in the times when we already have overgeneration because that's when the majority of its output occurs. So we're sort of cramming more and more energy into the periods when we don't need it to get a little trickle of energy in the periods when we really do. And this is the inherent challenge. The twin sides of the variability challenge for wind and solar is that they produce at the same time. And so if you want to get more energy from them in other times, you need to overbuild, which leads to overgeneration in the other hours in order to get a little bit more energy in the hours when it's really valuable. So now the marginal energy value has fallen such that we've lost 75% of the value for wind and 80% of the value for solar. And once again, the capacity value is basically nil. Now, what happens if we try to meet this constraint, not just with renewables, but even with our very expensive nuclear capacity that we had as an option that was many times more expensive on a levelized basis per megawatt hour than wind or solar? Well, surprisingly, the model actually picks quite a bit of that nuclear capacity to build and to complement the wind and solar. So instead of about 20% solar and 60% wind, we now have about 15% wind, and 15% solar, 15% nuclear, and 50% wind. And the nuclear is built because even though it's more expensive, its marginal value, its ability to produce energy during the times when we really need it, is that much higher. And the wind and solar has exhausted that value. So we actually see when we do this, the marginal value of the wind and solar increase a bit, right? So they're now back up to 43 and 34%. And we have a more balanced mix of resources. And we see that the nuclear can basically displace the remaining gas one for one because it can change when it dispatches its output. And it can concentrate its production in the periods when we don't have enough wind or solar to meet all of our demand and therefore need something else to help get rid of the fossil generation. And if we try to push the requirement to 90%, the share from wind and solar, from nuclear actually increases further. Because we're displacing more gas with nuclear that has very low fuel cost, the fuel saving value of the wind and solar in those hours when it's producing when the gas is gone, so when the orange is on the margin there, also falls. Because now in those hours, instead of displacing a gas plant with a fuel cost of $35, it's displacing a nuclear plant with a fuel cost of $2 or $3. So these are the kinds of complex interactions that happen in an energy system where different technologies are imperfect substitutes for one another. In certain hours, they displace one fuel, and another hour they displace another, and they complement or substitute for one another in ways that are not easy to predict simply by looking at the relative or average cost per megawatt hour of each of these resources. So even though we've succeeded in making clean energy cheap, my goal at the Breakthrough Institute, and making wind and solar some of the cheapest and often the cheapest forms of new energy, our job isn't done. Because we not only need to keep up the race between declining cost and declining value, we also need to figure out how to complement those resources with other resources that can produce value at times produce energy at times when it's more valuable. So if we look at the low carbon team and we think about the roles that need to be played, based on my research, I've proposed a new taxonomy for how to think about low carbon technologies, and that are divided into three wedges. The green wedge are what I call fuel-saving variable renewables. These are the renewables that are weather dependent, that vary in output on different timescales from minutes to hours to seasons. So things like solar PV or solar thermal, wind energy, run-of-river hydro dams that vary with stream flow, and even solar thermal with some amount of energy storage where you can smooth out the shorter-term variability but still have a seasonal variability component. And I call them fuel-saving because at a relatively high penetration level, the need for firm capacity, or the capacity substitution value, falls because it's the periods when we don't have wind or solar, or we have a drought and therefore don't have hydro, that drive our sizing of the firm capacity that we need. So they deliver most of their value to the system as fuel savers. When we have output from these variable resources, they displace the need for fuel burning resources like coal or gas or biomass, and they save that energy cost, and that's how they deliver value as part of the team. The second category in blue are what I call fast burst balancing resources. This is where energy storage batteries play a role, where flexible demand or demand rescheduling, like charging your electric vehicle at a time that's more advantageous to the grid, or demand response, which is curtailing your consumption at times when the marginal cost of electricity goes very high. So I have 2 window-mounted air conditioning units in my apartment. When it gets really hot, I turn them both on, but when I turn them both on, so does everybody else, and that's when the demand goes up. If I had an incentive to maybe turn one of those off for a couple hours, or pre-cool my building and therefore turn it off for a couple hours later during the day when prices are very high, I might be willing to do that. And that could significantly reduce the need for other generation resources that are rarely used. So these kinds of resources are valuable. They deliver most of their value by capacity substitution and flexibility. But they do so on short time scales. I call them fast burst resources. They can provide a fast burst of power. They're sprinters, but not marathon runners. And that's because they're either energy constrained, as in the case of battery, eventually you run out of juice in the battery, or because they have a very high cost to sustain that output, as the case of demand response. I'm willing to reduce my air conditioning load for a couple hours, but I'm not going to turn off my air conditioners for all of August when it's hot, right? I'm only willing to do that for so long. And that leads to the final category, which are firm low-carbon resources. Firm resources are resources that can be counted on to reliably produce power whenever we need them, regardless of season and over sustained periods of time of weeks or longer. So unlike the other resources, they're not variable and weather dependent, and they're not fast burst or constrained in their output. And these are technologies like geothermal energy, nuclear power, gas or coal plants with carbon capture and storage, biomass or biogas, or potentially combustion of hydrogen. I categorize these into two different categories. The categories are based on their difference in fixed or variable costs. The technologies on this side of the chart I call flexible base resources because they're ideally suited to running most of the time as a reliable base or foundation for our energy system, but are capable of ramping their output up and down to absorb available renewable resources when they're there to some degree. They're not as good at doing that fast as in the fast burst resources, so they're complemented by those battery storage devices or flexible demand, but they have some flexibility in their output. And then I have firm cyclers, which are technologies that tend to cycle on and off and have a relatively high variable cost, and therefore we only want to run them when they're really valuable. And a lot of times they'll sit and turn off, and we'll run them during periods when we don't have enough wind or solar and our batteries are fully exhausted. So we can see what this looks like for an example week in a very low carbon grid that is 99.99% decarbonized, at 1 gram of CO2 emissions per kilowatt hour produced. And this is an example for a Texas-like power system. And you can see the different resources each playing their correct role on the team. So you've got the firm low carbon resources, which in this case is a flexible nuclear power plant that can ramp down to half of its output over a relatively long time frame and then back up again. And then you have in green wind and solar production, so the big surge in solar every day, and then the wind, which is sort of undulating along on a different time scale. And then you have a range of fast burst resources, both batteries, demand flexibility, and demand curtailment that kick in during the afternoons when we really, when prices for electricity are highest and that capacity is most valuable, but only sustain that output for a few hours at a time. So they all work together as members of a team to meet our energy consumption reliably in every hour without any more than 1 gram of CO2. And you can do this with a zero carbon system as well. There's a little bit of brown there because this is the highest demand week. That's a gas turbine that is very rarely fired up but sits there as backup capacity in this example. What happens if we take one of those members of the team out of the picture? Well, this is what happens if we try to meet the same emissions constraint with only fast bursts, so batteries and demand flexibility, or fuel-saving variable renewables, wind or solar. You can do it. The model finds a feasible solution to this problem, but the system looks very, very different, not only from our system today, but also from the balanced system that I showed you in the last chart. The first thing to notice is that the y-axis is now twice as high, and we have these significant periods of overgeneration, where you're producing more than double what we're consuming, even on this peak demand week in the year. And you have to either absorb all that in energy storage capacity that you've built that is there and ready to suck up that extra energy, and use it then and discharge it every night for 8, 12 hours at a time, which is what you can see in the nighttime periods. Even then, it's not cost effective with energy storage to absorb all of that excess output. So the cross-hatched area is available wind or solar production that is simply curtailed or wasted, even though in this example we have very cheap energy storage batteries available and we build quite a lot of them. It just doesn't make sense on the margin to build that extra unit of storage capacity because it's not utilized enough throughout the year to pay off its costs. So you can do this, but I liken it to trying to play basketball with a team that only consists of point guards. Right? You can go out there, and point guards are great. They can dribble, they can shoot, they can pass, they can score. You can probably put points on the board, but you're going to lose every time to a team that has its star players in each of the right positions on the field, right, or on the court. My Chilean co-author likes to use soccer as his analogy, but it works just as well. And so, there are studies out there, and there are researchers who will point to feasible ways to meet our low carbon needs without the firm low carbon resources that I talk about, or without nuclear or gas or biomass. But it's feasible to do so, but it's much more difficult, right? And it's making our task, which is already daunting and challenging, that much more challenging. So in a recent paper, I explored a wide range of possible futures where we take account of the fact that we don't know what the cost of wind or solar will be in 2030 or 2050. We don't know whether new nuclear plants will come to market that are more cost effective than the ones we currently are struggling to build now, whether we'll have scalable carbon capture, whether we can harvest biomass sustainably, all kinds of uncertainties. So we ran nearly 1,000 scenarios through a detailed power system model where we looked at various emissions constraints, all the way from 200 grams per kilowatt hour, which is about a 70% reduction from current levels, down to 0. So 100 is about an 80% reduction, which is the kind of economy-wide goal that states like Rhode Island and Massachusetts have set. But as I mentioned before, electricity has to go furthest and fastest, so to meet an 80% economy-wide goal, we probably have to go much further than that for electricity, so we explore all the way down to 0 carbon. And we did that for both a northern system, which was parameterized based on weather and demand data for New England, and a southern system, which was based on Texas. So much better wind and solar resource, and a very different load profile driven by the different weather patterns in Texas, or demand profile. And we modeled a system where we included all three types of resources, fast burst, fuel saving, and firm resources under a wide range of combinations of different cost assumptions. And then an example where we take out all of the firm options. So no nuclear, no biomass, no carbon capture with gas, only fuel saving and fast burst resources, and if the emissions limit is not zero, some remaining natural gas plants. And as you can see, the cost rise dramatically as we proceed towards zero emissions in the case where we remove the firm resources from the mix. Whereas when we keep them, costs are not only lower, but the spread in costs is lower as well, which means that the eventual cost of reaching a low carbon grid is much less sensitive to the technology uncertainty that we face than it is if we rely on only a subset of our resources. And if you think about that, it makes sense. I'll come back to a stylized example of this in a few more slides, but this is betting on a narrower set of technologies to get there, which means that cost reductions for those technologies become much more important. Whereas in the other case, we have more substitutes, more players on the bench able to step in if our star players get hurt and can't perform, right? And so we have more redundancy, less risk, less uncertainty. So lower cost and less risk, both for the northern system and for the southern system across all scenarios that we studied. Which is a remarkably robust finding. Which resources play the firm role differs depending on our assumptions. Sometimes it's nuclear, sometimes it's gas with carbon capture, sometimes it's biomass and biogas with a lot of wind and solar because they pair together well. The point is we don't know today what that right mix is, and we don't know the level that will depend on each individual technology, but we can robustly say is that we need all three of these roles to cost effectively decarbonize, and we need one or more technologies to be able to get off the bench and play that role on the team. And this holds, as I said, across 1,000 cases that span a wide range of technology uncertainty, 2 different regions with very different resource quality and potential, a bunch of sensitivity cases where we made a lot of our demand flexible and reschedulable around the needs of the power system, where we interconnected these 2 very different regions with free transmission capacity so that they could share wind and solar output and demand that vary at different time scales, and where we added very long duration energy storage options that don't commercially exist today. So, what conclusions can we draw from this work as well as a survey of other research that I've performed recently? Well, in the near term, I think we can be very confident that wind, solar, and batteries, are, as well as to some degree natural gas, are going to drive continued emissions reductions. We were talking earlier that in New England, we've already driven the transition from coal to natural gas. So I think the role for natural gas here in New England is no longer substantial in terms of driving further emissions reductions. But across much of the world and much of the country, there are still a lot of older coal plants that could be displaced by gas and reduce emissions, the same time that we scale up wind, solar, and batteries to drive deeper emissions reductions. So over the next decade, I think the vast majority of the work to decarbonize our electricity system will come from these technologies, and that's thanks to the cost reductions and the improvements in these technologies we've seen over the last decade. But fully decarbonizing our electricity system is going to require one or more firm low-carbon substitutes for natural gas. In regions like New England, where we've completed this transition, and elsewhere as we continue to complete it, we're going to need to start displacing our natural gas combined cycle power plants, which are the current workhorses of the regional grid. And we need to do so in a way that fills the firm low carbon, or the firm role that they play in our power system today while emitting lots of CO2 with a firm low carbon substitute. And we need to do so at the same time that almost all of our nuclear power plants are going to reach the end of their operating lives over the next 20, 30 years because most of them were built long ago. So we have to either upgrade them and continue their operation, which has a cost, or we have to replace them entirely at the same time that we're trying to lower emissions. So our largest source of low carbon power provides 1/5 of our electricity from current nuclear power plants, about double what we get from wind and solar combined, has to be replaced as well. So we have to sort of run even faster to make progress towards zero carbon as those technologies or those power plants come offline. The challenge is that all of our firm low carbon options face multiple obstacles to their deployment today that we need to treat seriously. So reservoir hydropower plants are one option. So if you have a very large reservoir that can handle seasonal variabilities and ride through droughts, like they have in Quebec or Norway, you can use that as a firm low carbon resource because you can hold the water and use it to step in when you don't have enough wind or solar. Now here in New England, we've been trying to connect to Quebec to tap into that resource and to help replace the retiring nuclear plants in the region, but we've been unable to build the transmission capacity to figure out routes through the northern states in the region that everybody can agree to allow the southern states to connect to those sites. So that's challenging. And it's only a regionally available resource in a few places, and it's unlikely we're going to build a lot of new big reservoir dams, which have their own significant environmental impacts. Geothermal at the moment is severely constrained, again, to particular locations. I'll talk about another technology, engineered geothermal, that could unlock some of those constraints, but it's pre-commercial. Nuclear, as we mentioned, is extremely costly and challenging to build at the moment in the Western world. Same with gas and coal with CCS. And then biomass and biogas are our most widely scalable firm low-carbon options today, but face a variety of sustainability concerns. Anytime we use land to produce biomass, we're taking that land out of useful production for other agricultural purposes, which can compete with forestry and agricultural needs for food. There are questions about the life cycle CO2 emissions from forest biomass as we cut down stands of trees that are actively absorbing CO2 and replace them with younger stands that don't absorb as much CO2. So we incur a bit of a debt as those trees grow back, and depending on the cycle, the forestry management techniques, and the location of those trees, using solid biomass may actually be as bad or only marginally better than coal from a CO2 perspective. So it may actually not be a low-carbon alternative depending on where the feedstock comes from. So how do we fill out the team and get the technologies we need so that if wind and solar and batteries drive much of our decarbonization over the next 10 years, these technologies are ready to come off the bench 10 or 15 years from now and finish the job? Well, there are a few candidates that I think we really need to be serious about driving down in cost and improving their performance so that we can expand our firm low-carbon toolkit. The first are advanced nuclear reactor designs. There are a number of different designs that are both iterative improvements of light water reactors, which is the conventional type of reactor design we have, as well as a range of non-light water designs. The newer light water designs are what are known as small modular reactors. So one of the challenges with building new nuclear construction is that they're incredibly large, incredibly complicated, costly construction projects. And we're not very good at building large construction projects in the United States or the Western economies anymore. We built out all of our infrastructure decades ago, and we've simply gotten out of practice. We don't have the supply chains or the experienced staff to produce these sorts of things or manage this construction at that scale well. And it's not about nuclear specifically. Just look at things like the Big Dig or the San Francisco Bay Area Bay Bridge expansion or replacement. These kinds of infrastructure projects routinely go over budget. So a number of companies are trying to pursue smaller modular reactors that can be manufactured in factories under a factory setting and then shipped to site and very easily assembled. And rather than a 1,000-megawatt nuclear plant that can provide power for a city of 1 million people, they're talking about 50 or 60-megawatt nuclear power plants, and we'll build 6 of them or 12 of them on the same site, which gives us a plant the same size as a natural gas combined cycle plant, and we can substitute one for one. The first company to move through the NRC, or Nuclear Regulatory Commission, licensing process is known as NuScale. They're out of Oregon, where I'm from, so I'm rooting for their success. But they're moving through this licensing process and expect to complete that in 2020. There are other companies that have more advanced designs that don't use light water techniques. They're inherently safer and therefore may be able to get rid of some of the costly protection systems that need to go into light water designs to ensure that they're fail-safe. So they are further down the line, but may also be fundamentally cheaper than the designs that we're using today. And there are multiple companies pursuing that as well. The second one that is potentially impactful is a renewable resource, engineered geothermal energy systems. So to do geothermal today, you need 3 things in the same location. You need very hot rocks under the ground, usually near some kind of volcanic activity where you have magma extruding closer to the surface, which is why you find them around the Ring of Fire in earthquake-prone regions or volcanic regions. You need naturally porous rocks to circulate water as a heat transfer fluid through that hot area, and you need water in the same site. You either need to be able to pump it in or you need to have it naturally occurring. And finding all 3 of those things in the same place is very rare, and it's also very risky to try to find it. You have to drill a lot of dry wells before you find the right spot. And that's why current geothermal systems are relatively limited to places like California or Indonesia or the Philippines, and not widely used. However, we've gotten very good at drilling very deep wells that then go horizontal for very long periods of time and using hydraulic fracturing to create porosity in rocks and then circulate water through theirs to, in the case of today, extract. Right? right? Fracking for natural gas and oil in shale. The same type of technology could be used to create engineered geothermal energy systems where it's a different geology. We're not fracturing shale, but rather other formations. But you can use a similar technology to create the porosity that you need in the rocks and to pump water through in injection wells and back out production wells in a closed loop to produce steam and generate clean, reliable electricity. This is a pre-commercial technology. It's something that I think has a lot of promise in a country that is very good at drilling holes in the ground. There's one thing we're still very good at. And could be used to extract, as I mentioned, a clean renewable energy source where all you need is to drill deep enough to tap into hot enough rocks and to be able to create the reservoir and the porosity that you need to extract that heat. This could be done initially at locations very close to existing geothermal wells where we already know we have the hot rocks but have a limited existing geology to produce it. So that's the first places that are targeted, and those are mostly in the West. But much of the West has relatively shallow hot rocks that could be tapped into, and if we get good enough at drilling deep enough, you could even do this anywhere in the world, hypothetically. You go down deep enough, the rocks are hot enough to produce temperatures for steam production. And then the next category is carbon capture and storage. And as I mentioned, this is still pre-commercial, but there are a number of demonstration projects that have been much more successful than the Kemper project that I put the headline up for earlier. Both for capturing emissions from coal or gas plants, as well as fundamentally new ways to combust natural gas, a project called Net Power, which is being commissioned outside of Houston right now, that can produce, they can basically burn natural gas without any emissions, either air pollution or CO2 emissions, produces a pure pressurized CO2 waste stream along with water, actually drinkable, potable water, and that CO2 can then be, that pressurized CO2 can then be pumped to saline aquifers or depleted oil or gas wells and sequestered permanently. And so there recently a federal tax credit was passed called 45Q that will reward carbon capture and storage with $35 per ton for projects that sequester and use the CO2, either to pump out more oil for enhanced oil recovery or in other industrial materials, and $50 per ton if they permanently sequester that. And much like the production tax credit for wind or the renewable energy credits at the state level that it drove wind and solar forward in the early years, it's expected that this tax credit will drive a lot of catalytic activity in the industry over the next 6-year window when this tax credit is eligible at the moment. And so we're likely to see a lot more projects move forward and a lot of learning and improvement in the techniques needed to capture CO2 at a very timely moment. And finally, I should mention that batteries are not a substitute, as I mentioned, for firm resources, but rather play this distinct role as fast burst resources because they're simply too limited in terms of how much time they can produce output. So lithium-ion batteries are getting very cheap. We're using them in electric vehicles, so there's a nice complementary market that's helping drive improvements in the technology and scale up in manufacturing. But those batteries are very good really only for 2 to 8 hours or maybe 10 hours of storage. So they're very good for that fast burst of power within a daily cycle, but not for sustained output over the time periods that would substitute for firm resources. However, there are companies that are developing various methods for ultra-cheap, long-duration energy storage, sometimes known as seasonal storage, that could potentially obviate the need for firm generation because it has the same characteristics. It's not weather dependent, it can sustain output for weeks or more at a time, and it can be relied upon in any season. To do so, however, you need an order of magnitude cheaper energy storage medium. And so electrochemical batteries that we're using for other things like our consumer devices and our electric vehicles are not the route to do that. We have to pursue other routes that use thermal storage, that produce hydrogen to store energy or upgrade that to methane, or have some very, very cheap storage, electrochemical storage medium that currently is not commercial. So where do we stand today? I think we actually have somewhat of a fork in the road where many advocates and even some academics are urging us to go down one path, which is the path where we push renewables to the limit. And we say, you know what, the other things you just mentioned are fine, but they're all difficult, they're all challenging, and it would be easier for us to just solve the challenges associated with a high renewables future and put our efforts behind that. And any money we spend on the other stuff is wasting our time and effort, which I understand that argument, given where nuclear and biomass and CCS and others are at today. So let's talk about what it would take to push renewables to the limit and go down that path, and then we can sum up by thinking about which route seems more challenging. So If we push renewables to the limits and we just rely on fuel-saving variable renewables and fast-burst resources, storage, to get the job done, if you look at the literature, there are a number of papers that outline paths to do just that, right? So it's feasible. But there are a number of features in each of those strategies that have to fall into place for this to not only succeed, but to succeed in a reasonably affordable way. Usually still a bit more expensive than if we had a more diverse path, but maybe not an unaffordable route that could imperil the substitution of gas or of electricity for gas and oil. So the first feature is that almost all of these studies involve a continent-scale transmission grid, expansion of our existing transmission networks, to do two things: tap into the best renewable resource quality across the country, wherever it is, such as the desert Southwest for solar or the Midwest Great Plains for wind, and move that energy to where it's consumed, which is typically not the same place. We don't tend to live in the most sunny or windy locations in the country. And this is true in different continents, not just the United States. So studies for the US or Europe or North Africa or elsewhere envision building these very large-scale transmission interconnections that tap into the best resources and also help smooth out the variability of weather patterns, so that it might not be windy in New England, but it might be windy in Kansas, and if we can move power from New England to Kansas, we can then share our capacity across the continent and help address some of the variability challenges with wind and solar and reduce that overgeneration. However, as I mentioned before, it's been very difficult just here in New England to build a transmission line to Quebec, let alone to Kansas. And even in the Midwest, where you have a lot of wide open land and great resource potential, there have been a number of projects that propose multi-state expansions, a series developed by a company called Clean Line Ventures, including one that had backing from the Department of Energy, and things looked like they're about to fall into place. But it was going to link from Oklahoma to Tennessee, and it had to pass through several states in the interim. And those pass-through states eventually blocked construction because they don't benefit very much from having the transmission line run through their state. The importing state benefits, the exporting state benefits, but the states in the middle don't. So we had this really, even though most of these studies show that transmission is relatively cost-effective, we have a difficult siting challenge and a difficult collective action challenge and a difficult cost allocation challenge that in practice has prevented really anything on the scale that we see in these studies. So we'd have to overcome that hurdle if we want to do this. The second is that all of these studies include usually much more energy efficiency to reduce consumption, particularly during the peak demand periods or when the periods when we don't have much wind or solar output, to make it easier to meet our needs with renewables, and much greater demand flexibility. So we start to reshape our energy consumption around the availability of supply rather than the other way around, which is how we've run the power system forever, which is that we shape our supply around the variability of our demand. I think we can get some greater degree of demand flexibility, and there's a lot of cost-effective opportunities to do so, but once again, how far we can push that, what behavioral challenges we need to overcome to get people to start to think differently about how they consume their energy, a variety of obstacles to energy efficiency improvements that have existed for decades around principal agent failures and the landlord-tenant problem, where I might rent my building and therefore pay my bill, but the owner of the building controls whether they put in a new boiler or new windows that are more efficient, et cetera, and have split incentives. So there's a lot of different challenges to these things that have impeded their progress in the past, and we need to be able to overcome those as well to get to the kinds of scenarios in these studies. Third, we need to see extremely cheap wind, solar, and batteries. So we need to see continued cost declines to keep up the race between declining cost and declining value. And because we're pushing these technologies so far, their value declines precipitously. So in order to keep pace with that, we need to see very, very significant cost reductions, much more so than in cases where we harness wind and solar at a much greater scale than today, but in a balanced portfolio where we don't push them quite so far, quite beyond the role that they're meant to play in the energy system. And fourth, we would need some kind of seasonal energy storage technology if we fully want to issue any kind of firm low-carbon generation. So we need to have firm storage instead of firm generation. And that means we need to be able to take advantage of those seasonal overproduction of wind and solar that occurs in the summer particularly, absorb all that and hold on to it for months at a time, and then sustain output for weeks in periods in the winter when we don't have very much sun and when we have high pressure fronts that leave our wind output very low and can last for days or weeks at a time. Those are really challenging periods for these models. And they have to have some kind of seasonal energy storage, whether a thermal energy storage source that they can then be converted back to electricity, or hydrogen that can be produced electrochemically and then converted back to electricity later, or some other medium. And it has to be an order of magnitude cheaper than even the lowest cost estimates for lithium-ion batteries that we are likely to see. So to sum up, we need strategies today that are robust to risk. We cannot afford to fail in decarbonizing electricity and doing so affordably, as I mentioned. If we fail in either of those tasks, we may imperil our efforts to decarbonize the climate as a whole, or to decarbonize the economy as a whole and confront the climate challenge. And because we don't know exactly how the future will play out, we don't know which technologies will succeed, which will become cost-effective or not, we need strategies that are robust to that uncertainty and risk, and hedge our risks. And so I'm going to wrap up with a probability example. If you've taken a probability class, some of this will be familiar, but a way to think about a robust strategy in the face of that uncertainty. So let's think about two different strategies. One is the route that I just mentioned that tries to push renewables, wind and solar, to their limits and relies on several different things happening simultaneously. So a continent-scale transmission expansion, highly flexible demand and more efficiency gains to shift demand out of the periods when we don't have very much wind or solar, very low cost reductions for wind, solar, and batteries, and some order of magnitude cheaper seasonal storage option. All of those things have to happen. So it's a little bit like rolling a dice and having to roll this, to never roll a one and keep rolling forever, right? Roll a bunch of different times without ever rolling a one. The other alternative is that we pursue several different potential substitutes, only one of which needs to succeed. Affordable nuclear, affordable CCS, some kind of sustainable way to harvest biomass, or engineered geothermal that can unlock its availability across the country. Now those may be challenging individually, but only one of them needs to succeed for us to have to fill out the rest of the team. And with only modest reductions in the cost of wind and solar and storage, which I think are fairly guaranteed at this point, our models show that we could get the job done and affordably decarbonize with one or more of those options. So if you think about that, if we roll the dice and we say we have an 85% chance, which is basically rolling the dice and rolling anything but a 1, and you have to roll 4 dice, and you have to not get a 1 any of those times. The odds are 85% each time, but you have to multiply those by each other because they're contingent, they're joint probabilities. All 4 of them have to happen. So you have to get the 85% chance 4 times in a row. And if you do that, it's 85 to the 4th, 85% to the 4th, which is 52%. So we've gone from rolling the dice and having a 5 out of 6 chance of succeeding on any individual to nothing better than a coin flip, right? Because we need all of these things to fall into place to succeed in this path. In the other paths, let's just assume we have a 50-50 chance of those succeeding, much more difficult individually than any of these other individual tasks. But because they're substitutes, we only need one of them to succeed, which means that the odds of only one of those happening, which is 1 minus the odds of none of them happening, is 94%. So we've gone from a coin flip to something that's almost guaranteed. And of course, the best scenario would be to do both of these things, right? To pursue the efforts to overcome the challenges to a fully renewable grid at the same time that we pursue our efforts to expand and improve the firm low carbon resource set that could complete the job. If we do that and we add those joint probabilities together, we now have a 97% chance of success. Right? So individual opportunities may fail, but the overall venture can succeed robustly despite that uncertainty. Now these are entirely made up odds. I intentionally made them so that we took things that were a coin flip and turned them into really good odds, and took things that were really good odds and turned them into a coin flip. So I encourage you to think about your own odds that you would place on each of these bets. I'm thinking about creating an online calculator that would let us play around with that. But this is the kind of strategy and the kind of thinking that we need. There are strategies that on paper can work, but only if certain circumstances fall into place. And we live in an uncertain world, and we cannot afford to fail. So we need strategies that are robust and that stay open to the possibilities that are in front of us, and avoid locking into a single path. So I'm going to skip this one and leave it there. Thank you.
Okay, thanks very much, Jesse. Fantastic talk. So we've got a few mics here, and it'd be great to get a little bit back and forth to tackle our energy Ronin here, see if we can unpick the discussion. So we've got a mic there. If you just want to put your hand up, we'll...
Oh, hello.
Hey.
So I guess in our class, we just discussed a reading about sustainability that set up like 5 core principles that sort of prefaced it as a consciousness of cradle to cradle. And so if I'm thinking like the beginning of your presentation focused a lot on the economics of like reaching near zero carbon energy. Like if I was thinking of the end game, like the end game would be that we have like nearly free like energy that is like carbon free. And so I guess it's like a question more of like peeling away from the economics and like the calculations, but like sort of if all energy is free, if we actually reach the end goal of the intended like objective, like what does the definitions of value you have within your metrics, like how does that change? And like, I guess like if our current system of fossil fuels is like a vertically integrated system, like how do you see that changing? Like I would imagine like every house like becomes a mini power plant and like the system is like evenly distributed, and so who owns the means of producing energy, and like what's the role of companies after?
So energy is the master resource, right? It's the input to pretty much anything, and with free energy we can produce almost anything. So if we start from a world where we have free energy, we have a lot of freedom to make all kinds of choices. I don't think that's the end goal. I don't think that's the world we're headed to. And even if the energy output from a solar facility, for example, is free because it doesn't use fuel, the solar panel is not free, and it needs to be produced and it needs to be paid for somehow. And as I mentioned, we need a system around that solar so that even if solar is really cheap, the system as a whole is unlikely to be, I would say it's unlikely to be cheaper than energy is today, where we exclude most of the externalities that we don't price. In a world where we have displaced coal and natural gas, we'll have probably increased the price we pay on our electricity bills, but dramatically reduced the cost that society pays, both due to climate change, but also air pollution and water pollution and public health impacts from fossil consumption and production, so that the societal bill is smaller, but the bills on our, that we're actually paying and our energy bill might go up a little bit. My work tries to focus on making sure that that increase isn't too much, because we've externalized those costs for a reason, because we can, society can get away with it, and powerful people can get away with externalizing that and putting those costs on other people in ways that are either less salient or they're not able to defend from. And I think that those constraints, at least in the near term, are very real on the pace of transition towards a low carbon economy. And so if we dramatically increase the price of energy, there's a consumer backlash that could stop that process. And so I'm more worried about the near term, where we're actually going to increase the cost of energy rather than have free energy. If you fast forward to the future, maybe we're in a world where solar is, something you just paint on any surface for relatively free, and we have so much of it, it's okay wasting 98% of it and only using the 2% we need at the time where we need it. And that could change a lot of opportunities. And then you could have every surface on your house covered in solar panels, and you could charge your vehicles with that, and you could use it to power cottage industries and trade that production. But that's a long way from where we are today, and it's not, honestly, it's not really the challenge that I think our generation is going to face. I think our generation is going to face the challenge of getting to a world where we can actually envision something like that, where we've gotten rid of the most substantial impacts of fossil fuel production, where we've mitigated the worst impacts of climate change, and we have a relatively sustainable energy system that gives us the foundation to continue improving the means of energy production and moving in that direction in the longer term.
Yeah, so what I'm curious about is, let me try and marshal my thoughts. I guess what I was curious about is you talk a lot about using technology to get us to bridge that gap and to get us to like a decarbonized future. And I'm curious if you could speak from a policy perspective. I'm wondering if there needs to be like a pretty fundamental shift in how policy is passed and how we approach things from a policy perspective. It seems like that might be kind of necessary, both to kind of bridge the gap of your firm low carbon resources to get to to really, I guess, subsidize those resources because they seem to be so necessary, but then also to kind of really shift how externalities are displaced, because I mean, I would argue that in a current like kind of capitalist system, externalities will always be displaced in an unfair way. So I'm wondering if, do you think that this technological innovation will have to come hand in hand with pretty dramatic policy transformation, and maybe an example or two of some policy that could fit into our existing system now?
Yeah, I guess I spend most of my time trying to think about how we can accelerate this process from where we are now, which I think, just given the way I then constrain my thinking, which maybe isn't the right way to think about it all the time, I tend to think about the current sort of political structures and political constraints that we are in now, and how we can jujitsu those a little bit to get this process started where we have positive feedbacks. And I think about two very different types of feedback loops that I think are really important when you're trying to design policy that can help us tackle these problems that appear insurmountable given our current political constraints today. Like, we're not gonna wake up tomorrow and just be like, ban fossil fuels, you know, even if that would make this a lot easier. And the two types of feedbacks that I focus on a lot are technological innovation feedbacks and political economy feedbacks. So the first is mostly what I talked about here, which is that, you know, if we can do things today that make clean energy substitutes cheaper and more compelling as substitutes for our incumbent fossil fuels, it'll be easier politically to drive their adoption. It'll be easier to see companies with social responsibility pledges and ethos, you know, make that commitment to pay just a little bit more to do that. It'll be easier for individuals to sign up for to pay 20% more for, you know, renewable energy, or rather than 300% more. You know, it makes all of those sort of behavioral and political changes easier. And I think that lever has enormous power, because if you think about the kinds of cost reductions that we've seen, just since 2009, 70% reduction in the cost of solar, 75%, you know, that means that for the same political capital, the same willingness to pay as a society, we can buy 4 times as much solar. And so if the constraint is current political will, we now get 4 times as much progress for the same, you know, political buck. And if you go back even further, the cost of solar has fallen like a factor of 100 since 1970. And so like you could, you know, extrapolate that. Whereas I'm skeptical in the near term that we're going to summon somehow 4 times as much political will to deploy clean energy, for example. So they're important levers, but the innovation lever is a really powerful one, because we can see dramatic cost reductions for technologies that make the political challenge much, much easier to make rapid progress. The second are the political economy feedbacks, which is that if you think about who has power today and who wins and who loses from certain policies, if you can avoid attacking the most powerful and strengthen those who will benefit from continued policy support over time, you can change that balance over time, because you can build up the political strength of new entrants to the point where in the future they're actual policy stakeholders that can carry some of this water themselves rather than just public interest advocates, and can then, and at the same time are taking market share from the incumbents and therefore are weakening their power. And so again, if you think about this example, we could have said we want to tax carbon, or we want to outlaw emissions from fossil fuels, and that would have been a direct assault on incumbents, right? What we did instead 20 years ago is we said we want to drive wind and solar, and we want to, which are tiny industries, and we want to do that with subsidies, right? So it's not coming out of the coal guys' pockets, it's coming out of all of ours, but because it's a small amount of money spread across a lot of people, we don't, you know, see it much. But we can give a very large subsidy to this small industry, and then we can drive it forward from nascency into a relatively powerful industry. And over time, it'll start to take market share, and the incumbents will pay attention, and they'll either try to co-opt that or they'll try to attack it or whatever. But by that point, it's a much more powerful sector. And I think that change has also had an enormous effect over the political landscape, because you look at bipartisan support, for example, for the production tax credit for wind or the investment tax credit for solar. Well, it's because if you look where the wind and solar is deployed and where it's manufactured, it's in a lot of places that are represented by Republicans and as well as Democrats. And so you've managed to create an industry that now has its own political interest in the continuation of clean energy policies that now is a force on the playing field to help counteract incumbents. And so I think a lot about how to work within existing constraints, change those constraints over time with political economy feedbacks, and how to get more from within those constraints with technological feedback. And I think that's how we're going to accelerate the transition over time, and do things that appear impossible today, but 10 years from now might not be so impossible.
So can I just follow up on that question? So could it be said that there's quite a frame around your analysis which very much accepts the the politics of the possible within the context of the given United States at the moment.
Yeah.
Whereas it might be observed that if we look at ecological modernising discourse in Northern Europe, there are modes of thinking about this which suggest it's not simply a energy transformation question. We have to go into the circle of, say, production, think about the circular economy, which we were talking about at lunch, and then we have the issue of the sustainable consumption. Then that takes us potentially into how we plan our cities.
Yeah, which I think is
densification,
that's the biggest piece, yeah.
And then this goes into thinking about cooling cities through landscaping or other modes of urban ecologies,
Yep.
which then potentially takes us into new agro-food systems, land use, etc. And so I'm just interested. I suppose I've got two questions. Why is it that the US energy analysis often forecloses the multiple circles of that kind of more extended view of transformation? And I'm just wondering if one factored in those further concentric circles, would that open up more options in your analysis? So would we,
question, yeah.
would we have more opportunities still at play, and the variabilities and the probabilities could be an even bigger sandbox?
Yeah, so I'll say I do. I mean, I had a sign over my desk, a handmade sign that we made during one of the Breakthrough Generation summer fellowships when I worked at the Breakthrough Institute in my office that said, politics as if policy matters and policy as if politics matters. So the idea is you can find all kinds of cynical political operatives who are just trying to win politically and really don't care at all about the politics or about the policy that they're trying to pass. And you can find all kinds of policy wonks and ideologues who know the right policy but have no idea how to get it passed politically. Or are willing to do things to get a policy passed that have long-term political ramifications that prevent further policy passage, right? So there's this feedback between how you choose policy, cognizant of the political constraints and feedbacks that you exist within, and how you conduct your politics, cognizant of the fact that you really need policy that actually works, right? And isn't just symbolic and isn't just something that wins for your party for that midterm. So that is the way I tend to think about it, is sort of thinking about these feedbacks between the two. And obviously, I come at it from an American perspective, and so what I think is possible is different from what somebody in Australia or Nigeria or India or China would. But I do think that same general mindset makes sense in any context where you need to be working within systems of power that exist. You need to be thinking about how to change them and evolve them over time, but you can't wipe them off the board right away, and you can't simply be playing to the politics. You have to be thinking about how to make tangible, actual political policy progress. In terms of why the discourse here has been so focused on energy supply, it's a really good question. I think in some ways it may reflect it's just off the cuff, it may reflect where the policy levers in this country are concentrated and where particularly the federal government has the most influence, which is mostly over technology policy, innovation and technology investments through various agencies like DOE and DOD, over regulation of fuels and production and things like that, and tax policy, which is where we drive most of our policy. The other things are much more diffuse and are unless you're thinking about driving sort of the circular economy through regulation, which is an option, are more emergent and have more moving pieces and are maybe a little bit more difficult to figure out where the levers are. One area I do think we neglect as a climate community or climate concerned community in the United States and maybe in Europe as well is urban planning and urban and regional policymakers. Because the built environment that we live in is so long lasting and shapes so many of our decisions in ways that we don't think about, and shapes the carbon intensity of our activities, and takes a long time to change. So if you're not working on it and you're not working on it steadily and you're not thinking holistically about it, you can, it can feel impossible to change and have long-lasting implications. But so much of the environmental advocacy work from the most well-funded organizations in the U.S. focuses on federal policy. Maybe it focuses as some state strategy in some of the biggest states, but it almost routinely ignores, city mayoral races or city council races or expert advice for urban planning offices or things like that. And when I think about, the big wedges of emissions, I focus on electricity, which is probably one that's amenable to that kind of federal and state policy strategy because that's where the levers are. But when you think about transportation and buildings, which are the two other big chunks, and then agriculture and industry, you know, those are fundamentally shaped by state building codes, by city zoning, by city planning decisions, by transportations, you know, regional transit systems, et cetera. And those are often outside of the realm of those policy decisions. And I think have been ignored by the kind of policy wonk and grassroots community more than they probably should. And that maybe is changing over time. But yeah, I think that there's a huge opportunity to expand the same kind of thinking to other sectors and just think differently about where the levers of influence are. And it's probably necessarily a more distributed strategy because there are many, many, many more decision makers involved in those kinds of conversations.
Hello. Thank you. It was a great presentation. I had a question regarding, us for the designers in the room.
Yeah.
You talk a lot about urban planning, looking towards the future and changing us as the users. Do you see that actual behavioral changes and, like the banana versus the burger, energy needs or times when we use energy could at all affect this in a profound manner in the short term? And whether those are feasible things to target?
Yeah, so there are a lot of, so if you think about how to make electricity demand more flexible, there's a lot of behavioral challenges there, and I think there's a lot of opportunity to use automation and well-designed products to put all that behind, like, so we don't have to think about it, because I don't know how much time you spend thinking about your electricity bill. Probably the moment you open it and you write a check and you click pay on your online system, and you think about it for like 3 seconds a month, right? So if we're relying on everybody sort of thinking about electricity as much as I think about electricity to sort of figure out the best time to charge their vehicle, I don't think it's ever going to work. But if we can take advantage of automation and artificial intelligence to sort of do that stuff behind the scenes, where I basically tell my vehicle, I need to go to work tomorrow, or it knows when I go to work because it knows my habits, or my thermostat knows my building's thermal response, right? So that it knows that when it turns on, it has this, sort of latency in terms of the temperature changes in my building, because when I'm not home, it conducts little experiments and it tests that without me, these sorts of things. And so it knows that I want it this temperature, but I don't care when the energy is consumed, so it's pre-cooling the building in response to prices and trying to save me a little money in my bill. Those are the kinds of products people, I think, would buy and would love to have, as long as you don't have to think about it and as long as they actually meet their preferences. The minute their preferences are not met, they hit the override button and they don't trust it anymore and they're not going to use it. That would be my guess. And so this is a really tricky design challenge and a tricky product design challenge. There are also some behavioral feedback things that can be done, through design. Like there's a lot of vehicles now that just have a little indicator button on the dashboard that tells you when you're not hammering on the gas and you're actually kind of in the ideal fuel economy mode. And there's been some good evidence that those have a significant behavioral effect, that people notice and they stop, being quite so lead-footed, and they get a 3, 5, 10% improvement in their gas mileage just from a little light, So there are things like that that are important. I think the really big behavioral changes at the city and regional level come from redesigning transit systems so that we can count on them in our lives in a different way. And I think a lot about what's going on in Cambridge and Somerville and Boston, where I live, where we had several traffic fatalities, several biking fatalities in 2015 and 2016, if I'm remembering correctly, in a short period of time. I think 3 fatalities at different intersections. And not that was necessarily statistically abnormal, but because it happened so rapidly, people paid attention, and city governments responded, and they started a task force and pledged to have no fatalities ever by some date. And they've been making progress. They've been hiring, transportation engineers and designers and trying to lay out protected bike paths and corners and better painting of things like that. And the way I've seen it proceed as a regular biker who knows that biking in Cambridge is by far the fastest way to get anywhere and by far the most dangerous thing I do with my life, is that, I appreciate that there's an extra block where I can go on a protected path and get off of the traffic. But it's, goes through 2 blocks, then it stops. And there's another one over there so I can't plan routes around that system because it's not a system yet, right? And they're not deploying it like a system. And so it's great for people who already bike, but if your goal is to get lots of people who don't bike now to change their behavior and their mode shift, patterns and start biking, it's not doing that job. And it won't until we have an actual system. In places that have deployed systems like Sevilla in Spain, where you can get anywhere in the city, on a bike in a protected path, more or less, that does dramatically change people's patterns and their behavior because they know they can safely count on getting their kids to school or they can go to work every day and they can do so safely. And you know, those are the kinds of like infrastructural planning and design decisions that most people don't think about. They just know they live in a city where they can get on their bike and do that or that they can't. And those things have really long-lasting implications for how people, you know, plan their behavior and their patterns. And I do think need to be thought about very holistically within a climate perspective because in New England, transportation is the biggest source of our emissions, and as we make more progress with electricity, hopefully, which is the number 2, it's going to stay by far the biggest challenge we have to tackle.
Great, thank you very much. So for reasons of time, I think we're going to have to wrap it up there. So what I take from Jesse's last response is we seem to need to locate a generation of climate literate people called designers who might be getting an excellent liberal arts and humanities education as well, who can collaborate with other people to build new possible low carbon futures. I'm just scratching my head though to know where to find these people.
Get to work.
Where are they? You know, so if you can help with that project, please identify yourself and stand up for those possibilities. Okay. So can we have a big round of applause for Jesse Jenkins?